In this first of a two-part video series, we'll work through a few extra examples of how to interpret multivariate models. We won't learn anything new here. Rather, we're just going to practice the principles of making meaning of data using visualizations and models. In example 1, suppose we wish to model bike ridership by weekend status and weather category. We've seen over and over now that our analysis will in part be guided by what type of data we're working with. Here, it's important to note that we have two categorical predictors. Now, there are a lot of reasonable approaches to visualizing this relationship and no rulebook to follow. Thus, a good practice is to narrow down the world of possibilities by first thinking about how might we visualize the relationship between ridership and just one of our categorical predictors. And from there, how to pull apart these visualizations into further subcategories. Next, we can formalize our visual observations of this relationship with a statistical model. To write out the formula for this model of ridership, we can read straight down the coefficient estimate column. In this particular formula, we can only plug in zeros or ones for the weekend and weather categories, depending upon whether or not we're actually interested in that category. Thus, this model only has 6 possible outcomes, one per combination of the 2 weekend categories and 3 weather categories, or one per group represented in our box plot visualization. At some point, we'll be able to look at model tables like these and more quickly draw meaning from the numbers, but this takes practice. One way to build intuition for a model is to use it to make some predictions. To start, let's predict ridership on weekdays with category 1 weather. That is, the reference levels of our 2 predictors. Plugging into our model formula, we start by keeping the intercept. We always keep the intercept because it provides the baseline or foundation of our model upon which everything else builds. Then, since we're interested in predicting ridership on weekdays, we plug 0 in for the weekend true coefficient, or variable. Similarly, since we're interested in category 1 weather, we set the category 2 and 3 variables to 0. The resulting prediction, the sum of these pieces here, is roughly 4,212 riders. This prediction is represented by the red dot at right. Pausing and reviewing this calculation reveals a theme. When using categorical predictors, the intercept, 4,211, the same as our prediction, tells us about the typical behavior of Y, here ridership, at our reference levels. Next, let's predict ridership on weekends with category 1 weather. Building upon the intercept, we plug in 1 for the weekend true variable. In doing so, notice that we incur a drop in ridership associated with weekends, specifically a drop of 982 riders. Moving along, we plug in 0 for the category 2 and 3 variables. The result is 3,230 predicted riders on weekends with category 1 weather, represented by the red dot at right. Consider a final prediction, that of ridership on weekends with category 3 weather. In this case, we incur a drop in ridership associated with weekends and a drop in ridership associated with category 3 weather. This combination of categories produces our lowest predicted ridership of only 869, represented by the red dot at right. Having paid careful attention in these prediction calculations, we now have some insight about the coefficients. The intercept value indicated the typical ridership when the weekend true, weather category 2, and weather category 3 variables were all 0. That is, when we're interested in the reference categories. Or translated into our particular scenario, we expect roughly 4,212 riders on weekdays with category 1 weather. Next, we observed that the weekend true coefficient indicates a negative bump in ridership on weekends. Specifically, on days with similar weather, we expect roughly 982 fewer riders on weekends than on weekdays. This is a theme. Categorical coefficients indicate differences or changes from the reference level. Visually, we observe this bump when comparing the weekday and weekend box plot summaries within any weather category. Similarly, the weather category 3 coefficient indicates a negative bump in ridership on category 3 days. On both weekends and weekdays, we expect roughly 2,360 fewer riders on days with severe category 3 weather than on days with calm category 1 weather. We observe this bump when comparing the category 1 and 3 box plot summaries within either weekend category. Moving on to example 2. Suppose we wish to now model bike ridership by temperature and humidity. Here, it's important to start by recognizing that there are two quantitative predictors. Thus, to visualize this relationship, we might start with a visualization of riders versus temperatures, and then include information about humidity using something like a color scale. Next, we can formalize this visual observation with a statistical model. Now, in this type of situation, when we have two quantitative predictors, the corresponding model formula gives us an equation for a three-dimensional plane, which cuts through the three-dimensional cloud of data points. Mainly, our three dimensions are defined by our three quantitative variables in our analysis. As always, this formula tells us about the typical outcome at any set of predictor values. For example, to predict the ridership on a 50-degree day with 20% humidity, we build from the intercept and then plug in 50 for temperature and 0.2 for humidity. Now notice that humidity, we plugged in 0.2 instead of 20, since humidity is recorded in our dataset on a 0 to 1, not 0 to 100 scale. The result is roughly 2,964 predicted riders. Visually, this prediction corresponds to the height of our trend plane at the humidity and temperature values of interest. Next, if we maintain 20% humidity, but bump the temperature up by 1 degree from 50 to 51, then the predicted ridership also bumps up to roughly 3,024. That is, when we increase temperature by 1 degree and not changing humidity, the expected ridership bumps up by 60.433, from roughly 2,964 for 50-degree days to 3,024 for 51-degree days. Not coincidentally, this bump corresponds to the temperature coefficient of 60.433. This too is a theme. Quantitative coefficients indicate typical changes in y when we increase the quantitative predictor by 1 unit. Beyond using it to make specific predictions, let's dig into the meaning behind our three model coefficients which define the model plane. First, since it doesn't make sense to see 0-degree days with 0 humidity in Washington, D.C., where our bike data is taken, the intercept isn't contextually meaningful here. It just tells us where this plane crosses the y-axis, or where this plane lives in our three-dimensional space. Second, we saw that the temp feel coefficient corresponded to an expected bump in ridership when temperature increased by 1 degree, from 50 to 51 degrees. This is true in general. On days with similar humidity levels, we expect 60 extra riders for every 1 degree increase in temperature. Visually, this coefficient corresponds to the rate of increase or incline when we slice the plane at any humidity level. We can similarly interpret the humidity coefficient. On days with similar temperatures, we expect roughly 1,869 fewer riders when humidity increases by 1 unit. Now, since humidity is recorded on this 0 to 1 scale, a 1 unit increase from 0 to 1, or a jump from 0% to 100% humidity, is really extreme. In cases like this, we can translate this rate of change to a more meaningful scale. For example, suppose humidity levels increase by 0.1 units, or 10 percentage points. For example, humidity might jump from 70% to 80%. In this case, we expect roughly 186.9 fewer riders. Visually, the humidity coefficient reflects the rate of decrease or decline when we slice the plane at any temperature. Consider a third and final example in this Part 1 video. Suppose we wish to model bike ridership by temperature and weather category, the first predictor being quantitative and the second being categorical. Thus, to visualize our relationship of interest, we might start with a visualization of riders versus temperature, and then use color to indicate the different weather levels. Similarly, notice that our singular model trend at left splits into three, one for each weather category. We can obtain the equations for these three lines by building a model and examining the model formula. The key to making meaning of this model will be plugging in the appropriate zeros and ones for the weather categories. So category 2 and category 3, while not changing temperature at this point. First, to obtain the trend line for weather category 1, we plug in 0 for both weather categories 2 and 3. Thus, these terms simply drop out of our model, leaving us with an intercept of negative 288.688 and a slope of 55.301. Next, to obtain the trend line for weather category 2, we plug in 1 for weather category 2 and 0 for category 3. Simplifying this equation, notice that category 3 then drops out, and the category 2 coefficient of negative 386.422 has the effect of bumping our intercept down by roughly 386 rides, from negative 288.688 to negative 675.110. Similarly, in the trend line for weather category 3, the category 2 coefficient drops out, and the category 3 coefficient bumps the intercept down by a whopping 1,919 riders, from negative 288.688 to negative 2207.702. These three trend equations are matched up to their corresponding lines here. It's important to take stock of the fact that these three lines have the same slopes, that is, they're parallel, but they have different intercepts. Translated into words, the equal slopes reflect an assumption that the rate of increase in ridership with temperature is the same no matter the weather category. And the differing intercepts reflect an assumption that on days with similar temperatures, we'd expect ridership to be highest if the weather were category 1 and lowest if it were category 3. The details are illuminated by the model coefficients. As usual, the intercept coefficient tells us something about ridership for the reference category. Specifically, it corresponds to the intercept of weather category 1. Thus, the intercept of our complete model tells us where the category 1 model line crosses the y-axis when temperature is 0. Again, not a meaningful value in this example. Second, in building the model line for weather category 2, we noticed that the category 2 coefficient indicated a bump or change in the intercept of the category 2 line versus the category 1 line, dropping it by 386 riders, from negative 288.688 to negative 675.110. In fact, Since the two lines are parallel, notice that this bump between the two lines is the same across the entire model, not just at the intercepts. Thus, at any temperature, we expect there to be 386 fewer riders on Category 2 versus Category 1 weather days. We can similarly interpret the Category 3 coefficient as a bump or change in the intercept of the Category 3 line versus the Category 1 line, dropping it in this case by 1,919 riders from negative 288.688 down to negative 2207.702. Thus, at any temperature, we expect there to be roughly 1,919 fewer riders on Category 3 versus Category 1 weather days. Finally, consider the coefficient for a quantitative temperature predictor. This is the shared or common slope for each of the weather category trend lines. As with any quantitative coefficient, this tells us about the expected change in y per 1 unit increase in x. Or in our context, for any weather category, we expect ridership to increase by 55 riders for every 1 degree increase in temperature. Now, this final slide just summarizes the principles that we've discussed throughout this video. To start, a linear regression model in general describes the trend of a relationship between a response variable y and some set of predictors, x1, x2, up to xp, where again we're using subscripts to just distinguish between different predictors. Then suppose we have the following model without interaction terms, something that we'll learn about in the future, but it's important to mention here. Then in this case, we can interpret the coefficients as follows, paying special attention, of course, to whether or not we're talking about a categorical predictor or a quantitative predictor. To begin, beta 0 is the y-intercept. It describes the typical value of y when basically all of our x's drop out of our model, that is, when all of the x's are 0. That means when the x's are 0, that the quantitative predictors take on a value of 0, and the categorical predictors are essentially set to their reference levels. So the intercept tells us about y when all of my x's are 0 and my categories are set to the reference levels. Next, consider some coefficient beta I for one of our predictors xi. Then if our predictor xi is quantitative, then its coefficient describes the typical change in y per 1 unit increase in xi, while at a fixed set of the other x's. That is, we're just leaving the other x's alone and changing xi by 1 unit. Finally, if xi instead represents a category of a categorical variable, then its coefficient describes the typical change in y when we move to this category from the reference category, again while keeping all of the other x's the same. Or in other words, a categorical coefficient compares that particular category to the reference level.